So we are pleased to have next speaker, Dominic Joyce from Oxford. He's going to teach us enumerative invariance in algebraic geometry and the wall crossing formulae.
So, thank you. I'd like to start by giving some credit to Takeru Mochizuki. So back in 2009, he wrote a spring lecture notes volume about enumerative invariance for coherent sheaves on surfaces, which was kind of aimed at understanding algebraic Donaldson invariance and algebraic Seiberg-Witten invariance. And reasonable portions of what I'm talking about are kind of stolen from him, or at least when I ran into a problem, I would go and read Mochizuki and work out what on earth he did, and then do my own version of it. So the problem with Mochizuki is that it's enormously long and completely unreadable. So I decided that as a service to the mathematical community, I would write my own book, which will be enormously long and completely unreadable. Okay, I'd also like to thank Yuji and Jacob, who have been helpful in lots of ways and were my co-authors on the kind of prequel to this project. Okay, so at the June meeting, I described a rather general conjectural theory of enumerative invariance in both algebraic and differential geometry, and their wall crossing formulae under change of stability condition, and explained that we had proved these conjectures for the case of representations of quivers without oriented cycles. So that you can see in this archive paper joint with Jacob and Yuji. So today I want to tell you about quite a lot of progress in this program. So I'm writing a reasonably long paper, possibly might call it a book, which is not yet readable by humans, but eventually it will prove these conjectures in most of the cases in algebraic geometry that I care about, with a few exceptions or kind of caveats later. I hope to have finished this document, at least have a preliminary version ready for the January meeting, although of course I probably won't have. I've also understood a number of things I didn't understand back in June, one of which is how to fit the Donaldson-Thomas theory of Calabi-Yau threefolds into the same framework as this invariance framework, and another is how to include algebraic Donaldson and Seiberg-Witten invariance of surfaces in the case when B2 plus is greater than 1. And I'm going to say something about that in the second half of today's talk. So I should warn you that I may be lying because I haven't finished all the proofs yet. I do keep running into small problems, which I then mostly fix. It's not impossible that I will run into a big problem and be unable to finish the job, but I do rather hope not. I'm pretty confident that I'm going to be able to prove everything I want in, let's say, everything other than the Calabi-Yau 4 cases. Okay, so the general situation I'm considering is really rather complicated. So I'm going to explain roughly what I'm doing, omitting some details and oversimplifying some bits. So the kind of structure of my paper is I give a rather long list of assumptions which I want my geometric setup to satisfy. Under those assumptions, I prove the existence of enumerative invariance, counting things in the problem for each appropriate stability condition, and that these invariants satisfy various identities, including wall crossing formulae, under change of stability condition. So now I'm explaining the assumptions I make and various of their consequences. Later on, I'll tell you various situations in which the assumptions apply, in particular categories of quiver representations or coherent sheaves. So firstly, I'm going to start with an abelian category over the complex numbers, satisfying a list of assumptions. So this is a category in which we expect to be able to form invariants which count semi-stable objects in A with respect to a suitable choice of stability condition. So an example would be the category A of representations of some finite quiver, Q, or representations of a quiver with relations, where the relations should be presented in a particular form with some given generators. So you need a presentation of your relations involving generators in order to be able to define an obstruction theory on the moduli stacks, and therefore to be able to find virtual classes for moduli spaces. Perhaps more interesting are categories of coherent sheaves on a smooth projective C-scheme X, which has some appropriate dimension restrictions. It could be a curve or a surface. It might be a Fano threefold, a Calabi-Yau threefold, or a Calabi-Yau fourfold. So those are broadly the geometric situations in which it's known how to define enumerative invariants. Well, there might perhaps be some relaxations of that. I'm not yet sure whether one can do curve counting of various kinds for general projective threefolds, for example. We can relax the condition that the scheme X is projective. We could allow it to be quasi-projective, non-compact, if we replace A by the category of compactly supported coherent sheaves. Okay, so once we've chosen our sufficiently nice abelian category A, we form two moduli stacks, basically moduli spaces of objects in A. So there's a usual moduli stack in A, which is going to be an artan stack of the complex numbers. And there's also what I call a projective linear moduli stack. So this parameterizes objects in A, not up to isomorphism, but up to isomorphisms modulo multiples of the identity morphism. There's then a projection of stacks pi going from M into the projective linear thing, which has fiber point mod GM. So this entire project is very stacky. If you're not happy about stacks, then tough luck. Basically, we have to work with stacks rather than schemes in this project. And stacks are more complicated in a number of ways. One of which is that at each point of the stack, you have an isotropy group, a stabilizer group, and these enter the geometry of stacks in a very important way. Okay, so I'm going to write K of A for a quotient of the Grothendieck group K0 of A. This could be, for example, the numerical Grothendieck group, with the property that the moduli spaces M and MPL split as a decomposition over all classes alpha in K of A of a moduli space M alpha, which is open and closed in M. So in general, the Grothendieck group K0 of A will be too big. It might well be of infinite rank. So we cut it down to something smaller. So some examples, we might choose K of A to be Z to the Q0, the lattice of dimension vectors of quivers, or we might take K of A to be the lattice of Chern characters of sheaves if we're going to take X to be a smooth quasi-projective sheaf and a quasi-projective scheme, and A to be curve X. Okay, I'm going to write C of A for what I call a positive cone. That is the sets of classes in K of A of all non-zero objects in E. Okay, another piece of data I'm going to need, but which I won't mention very much, is that I will require some functors F going from our category A into the category of vector spaces. These are used to define stable pairs moduli spaces. So for example, for coherent sheaves on X, our functor might take a sheaf E to the complex vector space H0 of E of N, if N is some n is large, so we're twisting E by some very ample line bundle and taking the sections. Okay, I'm going to want a perfect complex E defined on M cross M. I'm going to write E alpha beta for the restriction of that to M alpha cross M beta. This will be the dual of the M to X complex, and in general it will be a perfect complex. I have an Euler form, chi, going from chi of A, k of A cross k of A into the integers. This is biadditive. It's not required to be symmetric in this version of the setup. And chi of alpha beta is going to be the rank of my X complex. I also want a Baron-Fantecchi perfect instruction theory on my projective linear moduli stack. This has to be related to the complex E by the equation that the pullback of F to under the diagonal morphism, the pullback of F to M rather than projective linear M is the difference between the K-theory class of the trivial line bundle and the pullback under the diagonal map of E. So what's going on here is that, well, so this thing is X of E, takes a sheaf F to X of FF. The dual of X to FF would give you the cotangent complex or the drive cotangent complex of M. The NPL differs by M by a GM action, so this is kind of deleting the Lie algebra of GM broadly from the. So, well, basically, in our situations, the projective linear moduli stack has a natural obstruction theory which has this relation with the complex E here. This is going to be very important later because we use E to define a vertex algebra and a Lie algebra structure on the homologies of M and MPL, and this is a relation which ensures that wall crossing for virtual classes is nicely related to the Lie bracket on the homology of MPL. Okay, so there are variants on this in the case of Fano threefolds, Calabi-Yau threefolds, Calabi-Yau fourfolds, and so on, which I won't talk about today. Okay, next piece of data I need is some set of stability conditions on A. Technically, I want what's called weak stability conditions. So here, T and less than or equal to is some total order. For example, in simple cases, it might just be the reals and the usual order on the reals. But for Giesecke stability, say, T might be a set of the family of monic polynomials. And then Tor is a map from this positive cone, C of A, in K-theory, mapping into the total order T, which satisfies some seesaw type conditions. So an example might be slope stability functions for quippers, for example. And I'm going to write M stable alpha and semi-stable alpha for the open substacks of stable and semi-stable objects in A, in class alpha in C of A. Okay, so I'm going to need some important assumptions on my set of stability conditions. One of which is the MSS alpha, the semi-stable moduli stacks should have a properness property. For example, having a good moduli, a proper good moduli space in the sense of Jared alpha would be one nice properness property which would do. But the properness property I really need is that when the stable moduli space equals a semi-stable moduli space, I want then this moduli space be a proper Lie-Mumford stack. So if we combine that with this obstruction theory up here, then we know that this semi-stable moduli space, in the case stable equals semi-stable, this is a proper Lie-Mumford stack with obstruction theory. It therefore has a Baron-Fantecchi virtual class, which by the definition of chi here and this equation there turns out to lie in the homology of, let's say, the projective linear moduli stack in class alpha of dimension 2 minus 2 chi of alpha alpha over the rationals. And I require that any two stability conditions in my set of stability conditions should be related by a continuous path in a suitable sense in S, and there are a few issues around exactly what we mean by that and ensuring that it can be true. So one interesting consequence is that for high-dimensional high-dimensional coherent sheaves on things of dimension 2 or higher, I really want to be working with mu stability as well as with Giesecke stability in order to make this notion of continuity of stability conditions work nicely. And then that leads into complications about what's the appropriate properness property for moduli spaces of new semi-stable sheaves. But let's not get into that. And then finally, I'm going to want a finiteness assumption, which will ensure that there are only finitely many terms in the wall-crossing formulae. So for coherent sheaves on surfaces, you can prove this finiteness condition holds using the Bogomolov vanishing theorem for discriminant for moduli spaces of coherent sheaves and their discriminants. There are issues here to do with finiteness when dimension of your projective scheme is 3 or higher. Okay, so that's broadly the setting I'm working in. So as I've told you in more than one previous talk, under these kinds of assumptions, I can define the structure of a graded vertex algebra on the homology of the full moduli stack of M, let's say of the rationals. It has to have a shifted grading, so the portion of M in class alpha. No, that's right. Yeah, the homology of M in class alpha gets shifted by a -2 chi alpha alpha to get the grading right. And here is a complicated formula for the main part of the structure of the vertex algebra, this state field correspondence. And don't worry about that. Now, using this, you can then induce the structure of a graded Lie algebra on the homology of the projective linear moduli stack. And the shifted grading here is shifted by 2 - 2 chi of alpha alpha. So therefore, if you take the degree 0 piece of this graded Lie algebra in its shifted grading, that is itself a Lie algebra. And the degree 0 piece is the direct sum over all alphas of the homology of the projective linear M alpha here in dimension 2 - 2 chi of alpha alpha. Okay, so it's worth noting that when we can form a virtual class for a semi-stable moduli space, in the case in which stable equals semi-stable, it lies in this dimension. Okay, so our Lie algebra has selected for us exactly those, it's selected out, it's given us a Lie algebra containing exactly the right degrees to contain virtual classes, which is a nice fact. Okay, so here are the problems I want to solve. So, as I said, in the case in which stable equals semi-stable for your moduli space, then this moduli stack is a proper Lie-Mumfeld stack with an obstruction theory and a Barrett-Fantecchi virtual class in this homology group of the projective linear moduli stack. But if the stables are not equal to the semi-stables, so if there are strictly semi-stable sheaves in class alpha, then in general, this moduli stack is an Artan stack, not a Lie-Mumford stack, and the Barrett-Fantecchi virtual class cannot be defined. So I want to define an enumerative invariant here in the same homology group for all classes alpha, whether stable equals semi-stable or not. I'm going to write this as brackets with an invariant there rather than virtual. So then this invariant should be equal to the virtual class in the case in which stable equals semi-stable and the virtual class is defined, but this is going to be defined for all alphas. So that is, I want to define invariants which count strictly semi-stables. Now, for the moment, the virtual class is defined in a geometric way, starting from the data of the Deligne-Mumford stack here and its obstruction theory. My invariants here are not a priori defined starting from this stack and geometric structures on it. They're defined in some much more roundabout way, involving pair invariant moduli spaces and things like that. So you shouldn't necessarily think about this invariant as simply a invariant of that moduli stack. It's more complicated than that. So I'm going to want an explicit wall crossing formula for these invariants under the change of stability condition for t less than or equal to. Okay, so all of these goals are already known for Donaldson-Thomas invariants of Calabi-Yau threefolds, as in my work with Yan Song and Konsevich-Soberman back in about 2008. And also for other classes of motivic invariants in algebraic geometry. That would be my work around about 2005-ish. So what I'm wanting to do here is to extend this to invariants formed using virtual classes in homology, which are generally non-motivic. So motivic invariants in algebraic geometry are things which are kind of defined by an Euler characteristic style cutting and pasting thing, and they are local, kind of pointwise local on the moduli spaces. For a motivic invariant, you know what the contribution of each point in the moduli space is to the overall invariant. Whereas virtual class invariants are non-local, and they're only defined if the moduli space is proper, and then it's a kind of global contribution. Okay, so I'm going to regard these homology classes, the virtual classes, in the homology of projective linear moduli stack as being our primary invariant. So quite often people think about invariants, such as Donaldson invariants or whatever, as being numbers rather than homology classes. So if you want numbers, you can get numbers by integrating universal cohomology classes in the cohomology of the projective linear moduli stack over your homology classes. So almost always, in these situations, there will be some large collection of interesting cohomology classes in here, which form some understandable algebra, and you can then get numbers by integrating them over the homology classes you've just defined. It's worth noting that the homology of this projective linear moduli stack is often explicitly computable, especially in the case in which you actually take the moduli space, moduli stack of objects in the derived category rather than in the abelian category. Even if you can't compute this, there will be a nice Lie algebra morphism to another Lie algebra constructed in a differential geometric way, which is explicitly computable. So when we're trying to define invariants living in this homology group, we are able to essentially give coordinates on this homology group in which the invariants can be written in a nice explicit way. Okay, so here is a statement of the main results, at least in the basic case. So I should stress that this is work in progress and the proof is ongoing. So in this situation, we can define invariants in the for each stability condition. We can define invariants in this homology group of this degree for all classes alpha in the positive part of the K-theory with three properties. Firstly, if the stable is equal to the semi-stable for this moduli space, then the invariant is equal to the Berendt-Fantecchi virtual class. Secondly, these invariants have an explicit inductive definition via Berendt-Fantecchi virtual classes of moduli spaces of stable pairs in an auxiliary abelian category A bar, which is essentially an extension of the first abelian category by the category of vector spaces. And these, back in my assumptions, I had an assumption about the existence of certain certain functors, f going from A into the vector C. We use these satisfying some conditions. We use these to define these stable pair categories. And thirdly, if Tor and Tor twiddle are two different stability conditions, and alpha is some class, then there is a universal wall crossing formula, which is written in the Lie algebra, the Lie bracket on this H0 of MPL. So here, in the new stability condition Tor, the alpha invariant is the sum of over all different ways of decomposing alpha as the sum of n classes in the positive K theory of a repeated Lie bracket of other invariants for the old stability condition, Tor, multiplied by some rational combinatorial coefficients, u twiddle of alpha 1 up to alpha n, Tor and Tor twiddle. So these are explicit, or at least explicit-ish, and they depend only on inequalities of Tor and Tor twiddle evaluated on various combinations of these alphas. So they're basically entirely combinatorial objects, although they are somewhat complicated. And if you don't like this wall crossing formula, there is a Kontsevich-Soegman style version of the wall crossing formula, which just follows from this. So if you prefer the Kontsevich-Soegman way of writing wall crossing formulae, that's also available. Okay, so let me give some kind of very brief sketch of this. So the proof is going to be big and horrible. At a guess, the total proof will probably be greater than 100 pages. My current document is about 120 pages long. But let me give you a rough idea. So first we prove the wall crossing 1 for simple wall crossings, in which, all of the moduli spaces in the formula have stable equal semi-stable. So I'm thinking about having Tor and Tor twiddle on either side of a wall. And then on the wall, things are allowed to break up into exactly two stable factors in classes beta and gamma, let's say, where Tor of beta is greater than Tor of gamma, Tor twiddle of beta is less than Tor twiddle of gamma. Then the wall crossing formula 1 becomes this. The Tor twiddle invariant of alpha is the Tor invariant of alpha plus the Lie bracket of the Tor invariant of beta and gamma. And because in this situation all of these have stable and semi-stable, this is an actual identity satisfied by the Baron-Fantacci virtual classes. And this can be proved using GM localization, so the Graeber-Panday localization formula on a certain master space constructed from the alpha moduli space for the stability condition lying on the wall between Tor and Tor twiddle. Secondly, I introduce a bunch of auxiliary categories A bar, which are the extension of some subcategory of A by a category of representations of a quiver. And we can then define auxiliary invariants as kind of generalized stable pair invariants, really, counting objects in this auxiliary category. So if Q is just one vertex and this has, so that its representation is vector spaces, then this gives us stable pair invariants I've already mentioned in part B of question 1. But we need not just one category of stable pair type objects, we need a whole system of them parameterized by quivers. Okay, so far we've defined invariants both counting things in A and also counting things in these extended categories A bar using a notion of stable pairs. And the invariants are defined and are equal to the virtual classes when stable to semi-stable. And we can prove that the virtual classes themselves satisfy the wall crossing formula in the case of simple wall crossings. Okay, so there's also other ways of proving relations between these various invariants for different categories. So for example, if you've got a moduli space which has a smooth morphism over one of the semi-stable moduli spaces with fiber CPn, then that invariant determines this invariant by, you kind of take the cat product of this with the relative, the Euler class of the relative tangent bundle of the smooth morphism, and then you push it forward and you get n+1 times that invariant, and so on. So that gives us two kinds of relations between our invariants, one coming from simple wall crossings and one coming from smooth vibrations. And the idea is to get enough of these two relations to eventually prove the complicated wall crossing formula. So we prove that if Tor and Tor twiddle are sufficiently close in the set of stability conditions in some sense, then the complicated wall crossing formula can be reduced to a kind of finite sequence of simple wall crossing formulas and smooth vibrations in these by going up to these auxiliary categories. And then finally, so that would prove the wall crossing formula in the case in which Tor and Tor twiddle are in some sense very close in your set of stability conditions. And then for the general case, you join two stability conditions by a continuous path of stability conditions, and then you kind of go along this path in very small jumps, proving that the wall crossing formula holds from one thing to the next thing very close to it, and then because the wall crossing formula has an associativity property, you can kind of compose things to get all the way from 0 to 1. And you need a strong finiteness condition in this part of the proof to ensure that the wall crossing formulas continue to have finitely many non-zero terms. Okay, so some cases in which the main results apply, or at least I hope they're going to apply once the whole project is finished. Firstly, when A is mod CQ, for Q is equivalent with no oriented cycles, that condition gives us proper moduli spaces and with slope stability conditions. So that's the thing which Yuji and Jacob and I already proved. Secondly, for quivers with relations, where the relations are given some set of generators in order to define your obstruction theory, and slope stability conditions on these, provided the moduli spaces are always proper, or satisfy the properness condition. So having no oriented cycles on Q is sufficient for that, but probably not necessary. We could consider coherent sheaves on a projective curve. So in that case, the wall crossing formula is boring because there's only one stability condition, but at least this gives us a possibly new definition of counting strictly semi-stables on projective curves. Coherent sheaves on projective surfaces. Let's say with geometric genus PG equals 0, that's the same as B2 plus equals 1, for both Giesecke stability and slope stability, defined using real Kähler forms. And I'll talk about the case PG greater than 0 later. And then coherent sheaves on X if X is a Fano threefold. So this is, so when Richard Thomas defined Glanson-Thomas invariants originally, there were two cases, the Calabi-Yau threefold and the Fano threefold case. The Fano threefold case broadly fits into this Theorem 1 framework with a few caveats. Firstly, you have to exclude dimension 0 sheaves. And then secondly, you need to restrict to Kähler forms living in some small open ball in the Kähler cone in order to make the finiteness conditions hold. So let me have actually a quick aside on the finiteness conditions. So in general, it's not obvious. So let's go back to the wall crossing formula. Here it is. This is a sum. So alpha is some fixed K-theory class. We're summing over n's and ways of decomposing alpha into a sum of alpha 1 plus up to alpha n. And you may as well assume that in this sum, all of the moduli spaces here are non-empty, because if they are empty, that will give you a 0 term. Also, you may want to assume that this coefficient here is non-zero, because otherwise that would also give you a 0 term. So it's not obvious that in this sum, there are only finitely many sets of alpha 1s up to alpha n's for which that's non-zero and these are non-empty. So that's the issue I'm worrying about. So I don't think there's any good notion of convergence in this sum of homology. So therefore, if there are infinitely many non-zero terms, then the theory is going to break. Okay, so if you're looking at quivers or coherent sheaves on a curve, this is not a problem. You only get finite sums. For coherent sheaves on a surface, if alpha has positive rank, then a theorem by Bogomolov shows that if the moduli stack is non-empty, then the discriminant of alpha is non-negative, where this is some combination of C1 squares and C2s and so on. So then you can show that using this, you can show that the Wall-Costing formula has only finitely many non-zero terms. Now, in dimension 3 and higher, in general, I can't prove that the Wall-Costing form has only finitely many terms. But I can prove this if Tor and Tor twiddle are either Giesge or slope-stability conditions coming from real Kähler forms, which are sufficiently close in the Kähler cone. Now, actually, in my previous work on Joyce, Song, and so on, this was also an issue which I didn't really address. I just claimed at some point that I could prove this, and then never actually wrote down the proof and forgot all about it. But I have actually gone back and found that this is actually true. I will probably have to write up the proof this time. Okay, so then using this, you can transform between any two such stability conditions in finitely many steps, where each step has Wall-Crossing formulas with only finitely many terms. So that's about as good as one could hope, I think. Okay, so the theory I've told you about so far doesn't include Calabi-Yau threefolds and conventional Donaldson-Thomas theory, because although three Calabi-Yau moduli spaces do have a perfect obstruction theory, a symmetric obstruction theory on the semi-stable moduli stack, at least if the stable equals semi-stables, they don't satisfy the condition, which is part of my assumptions, that the pullback of F is the class of the trivial line bundle, take away this. In fact, in this case, this gets deleted, and the pullback of S is just minus delta of M star of E. But this was a condition which links the obstruction theory to the Lie bracket on the projective linear moduli space. And that is really what causes the simple Wall-Crossing formula involving Lie brackets to be true. So because of SCSHGAPW, actually the Lie bracket on this projective linear moduli stack is 0, because it involved a kind of E direct sum E dual, and the E dual cancels out with the E. Okay, but I now understand a way to fix it. So we introduce a degree -2 formal parameter y into the vertex algebra construction. So we make h hat star of m extended in formal power series y into a graded vertex algebra. Actually, a completed version of a graded vertex algebra, because you lose some infiniteness in these formal power series. If I go back to the so in this expression here, you have to split off that and this separately, and you have to split that and this separately, and these two, and then some of the z's turned into z plus y's. So basically, all of the z's attached to this bit turned into z plus y's. The z's attached to that bit turned into z minus y's. This stays as a z. So it's just a way of making this vertex algebra definition, including a formal parameter y in this formula. Okay, so then you now have this thing is a completed vertex algebra. The homology of the projective linear moduli stack extended by formal power series turns into a completed graded Lie algebra. This Lie bracket is a formal power series in powers of y with, let's say, square brackets y. I is the coefficient of y upper I. Now the leading term in this thing, bracket 0, is the previous Lie bracket, which, as I told you, is 0 because of the SCSHGAPW vanishing thing. So therefore, the subleading term, square brackets 1, actually induces a degree 2 Lie bracket on this thing when you set y equals 0. So because the first version of the Lie bracket vanishes, we can produce a second version of the Lie bracket on this thing, which has degree 2 in this shifted grading on that. So then we can use a version of the previous construction, which involves this Lie bracket. Well, if we shift the degree by -2, then this thing now becomes a natural graded Lie bracket of degree 0. Okay, so I hope this will reprove a lot of Donaldson-Thomas theory without using Baron, PTVV, BBJ, and so on, right algebraic geometry or critical loci. Okay, so that's not so interesting, but maybe there's potential for applications of that. For example, it's possible that this could lead to an extension of Donaldson-Thomas theory of Calabi-Yau threefolds in positive characteristic, although I have no intention of going into positive characteristic myself. Okay, another direction of extension is to Calabi-Yau fourfolds. So Richard Thomas and a postdoc, O, have put a paper on the archive this week about a virtual cycle construction for Calabi-Yau fourfold moduli spaces. So I hope to be able to prove the analog of this theorem for coherent sheaves on a Calabi-Yau fourfold using O. Thomas virtual cycles. And I haven't worked out the details, and I don't yet know whether all the properties of the O. Thomas virtual cycles which I'm going to need are going to be available, but I'll work that out when I come to it. Okay, so let me now move on to my next topic, which is how to extend this picture to coherent sheaves on surfaces with positive geometric genus. That is the case B2 plus is greater than 1. I should perhaps warn you that this part of the talk is more speculative or more likely to be wrong than the previous bits. Anyway, so let's suppose now that X is a projective surface with PG greater than 0. That is H02 of X is strictly positive, or B2 plus of X is greater than 1. So then, well, the theory I've talked about previously does actually apply to coherent sheaves on X. And it gives you invariance and so on, and apparently everything looks nice. But for the case of sheaves of positive rank, the obstruction theory you get on MSL on the semi-stable moduli space actually has a constant factor, the dual of H02 of X, in H minus 1 of the sheaf F. So there's a constant obstruction space which doesn't obstruct. This forces the virtual class, well, in the case in which stable equals semi-stable, this forces a virtual class to be 0. And because the virtual classes are all 0, the invariants which are built out of those virtual classes are also 0. So in this case, basically the theory is boring. We don't have any non-zero invariants for positive rank. Now, you can also define a reduced obstruction theory on the projective linear moduli stack, at least on the positive rank part, by essentially deleting the H02 of X part factor in the obstruction bundle. And if you form virtual classes using this reduced obstruction theory, so all this is well-known mathematics, then you can define virtual classes when stable class equals semi-stable class, which can be non-zero. So let's think about these reduced virtual classes as being algebraic U of n Donaldson invariants for your projective surface, because roughly speaking, U of n instantons are equivalent to holomorphic rank n vector bundles with Hermitian-Einstein connections, and these are equivalent to semi-stable algebraic rank n vector bundles. Okay, so therefore it seems natural, in order to include this PG greater than 0 case, to try and extend our theory to include invariants defined using reduced obstruction theories. Okay, so on the face of it, you would think that, well, we could define reduced invariance even when the stable is not equal to semi-stables, using the pair invariant method, which is true, and such that these reduced invariants would be equal to the reduced virtual classes when stable is semi-stable. But because we already know that when B2 plus of x is greater than 1, Donaldson invariants are independent of the stability condition, because the stability condition corresponds to the splitting of H2 into H2 plus and H2 minus, because H2 plus of x is basically the 2, 0 plus 0, 2 part of the cohomology, plus the parts spanned by the Kähler form, and the stability condition is determined by the Kähler class. So varying stability condition corresponds to varying the Kähler class, which corresponds to varying H2 plus. Okay, so naively, you would expect that in this reduced invariant case, the invariants are going to end up being independent of stability condition, and therefore there should be no interesting wall-crossing formula. And if that were true, that would be a pity, because wall-crossing formulas can be powerful tools for computations of various kinds. Now, I'm going to propose a more complex setup involving an abelian category A, which can have non-trivial reduced and non-reduced invariants at the same time, and can have non-trivial wall-crossing formulae for both. Okay, so in the case in which A is a coherent sheaves, then the non-reduced invariants are all 0, at least in positive rank, and because of that, the wall-crossing formula for the reduced invariants becomes trivial. But if A is a category of things that Mochizuki would call L-Bradlow pairs, basically a kind of pair invariant abelian category, then you can get both non-reduced Seiberg-Witten type invariants and reduced Donaldson type invariants, and then the wall-crossing formulae can be used to compute Donaldson invariants in terms of Seiberg-Witten invariants. So we can bring the kind of Seiberg-Witten implies Donaldson story into this this whole wall-crossing in abelian categories picture. Okay, so again, I ought to give Mochizuki credit here. Mochizuki basically knows almost everything I know, except for the Lie algebra wall-crossing formula. He kind of does that in a rather ad hoc way, which makes computations rather difficult. Yeah. Okay, so let's assume that we're given firstly an open substack m.pl of MPL and a positive integer d, and then a reduced obstruction theory, which is defined only on this open substack. So basically, there's going to be some part of our abelian category in which the definition of the reduced obstruction theory works nicely and gives us a perfect complex in degrees -1 up to 1, let's say, in the Artin stack case. But there'll be other parts of the theory in which the definition of the obstruction theory doesn't work. And that it's rather similar to what happens to Fano threefolds, for example. The obstruction theory is defined nicely except on dimension 0 sheaves when it has cohomology in long degrees. And the same thing happens here. You can define the obstruction theory probably on the entirety of objective linear moduli stack, but some cohomology vanishing things which make it into an obstruction theory in the right degrees only work on this special open substack. Okay, and we have a new condition of compatibility of the, sorry, I should say reduced here. We have a new condition of the compatibility of the reduced obstruction theory with the class, the complex E, which is used to define the Lie bracket on homology, which now we have a D+1 here instead of a D, basically because this D is compensating for the fact that we delete a trivial rank D bundle from the -2 cohomology of F to make the reduced F. Okay. Secondly, we're given a subset of what I call reduced permissible classes in here. So these are the classes where we're able to define the reduced invariants. and we require that if you have some stability condition and some reduced permissible class, then the moduli stack in class alpha should live inside this special subset where the obstruction theory is defined. And therefore, if stable equals semi-stable, you have a well-defined reduced class. And because we've got this shift in dimension of D, of a complex dimension of D, this now lies in H hat 2D of the projective linear moduli stack here. And then we have various conditions on these. One important condition is that if alpha is beta plus gamma and alpha is reduced and permissible, then one of beta and gamma is also reduced and permissible. So in some sense, a set of reduced classes is an ideal in this monoid. Okay, so then here is the main results in this reduced case, so which is work in progress or
there is an
What happened?
issue, right? He is frozen.
Yes.
Dominique,
Okay,
are you
sound.
back?
He may have to log out and log back in.
Okay, he disappeared. Okay.
Okay, so wait.
Okay, I just was concerned that there is yeah, something wrong with my connection, but that's
No. We'll see if he comes back. He should.
well, he has his iPad also. Yeah, connected as co-host.
Yeah, it's still there.
It also doesn't seem to be a Math Institute issue, right? Because Jason is still there. So
Yeah, well,
I think Marcus has gone to knock on his door.
yes,
Yeah.
oh gosh.
Did you find him,
So
Marcus?
Dominic's Zoom has crashed. He's just restarting it.
Okay.
Well, his pad still seems to be on, but anyway. Okay, let me make him co-host again, just in case. Okay.
You're muted.
Uh,
oh, okay.
okay, good.
Right. Right. Can you hear me?
Yes.
Okay. Right. Sorry about that. My internet died. I have no idea why. Okay. So here's the theorem in the reduced case. So as well as the usual invariants, I'm defining reduced versions of the invariants, which lie in this homology shifted up by dimension 2D. If stable equals semi-stable, they are the usual, they're the Baron-Fantecchi virtual class defined using the reduced obstruction theory. They also have an explicit inductive definition, which is different to the previous version, via Baron-Fantecchi virtual classes of moduli spaces of stable pairs defined using a reduced obstruction theory on the stable pair moduli spaces. And one of the interesting things now is this is the new wall crossing formula. So it has the same kind of structure as the old wall-crossing formula, except on the right-hand, so on the left-hand side, I'm computing a reduced class. On the right-hand side, it's a sum of repeatedly brackets of things where we have one reduced class and all of the other non-reduced classes. Okay, so in the so for example, in the case of if we just applied this to Donaldson invariance in curve X, then these classes, then the non-reduced classes would all be 0, and so this would end up being M alpha, that the Tor invariant would be equal to the Tor twiddle invariant would be equal to the Tor invariant, and there'd be no correction terms. But in general, that's not true. And then finally, if you have a reduced permissible class, then the original invariants are 0. So basically, we have a setup in which there's two kinds of invariants. We have the ordinary invariants, which are defined for all classes. We have the reduced invariants, which are defined only for some classes, and kind of ideal of the positive K theory. But when the reduced invariants are defined, the ordinary invariants are 0. Okay, so this reduced wall-crossing formulae is rather like the previous wall-crossing formulae. As I said, you'll get exactly one reduced invariant, another non-reduced invariance in each term. So the reduced invariants live in this H hat 2D of the projective linear moduli space, which is a representation of the, sorry, there shouldn't be alphas here. It's a representation of this Lie algebra where the non-reduced invariants live. And algebraically, you can think about the non-reduced wall-crossing formula relates to the reduced wall-crossing formula in the same way that algebras relate to representations. And so to prove this, actually the main new step is to replace the simple wall-crossing formula with a reduced version of the same thing, in which if something splits into two classes, then this happens basically. There's a kind of fourth case in which beta and gamma are not reduced, but that doesn't occur by the ideal property of this. And then once you know that you have to replace the simple wall-crossing formula by that, you kind of follow through the other steps and just modify formally in an appropriate way. Okay, so this can be applied to the kind of algebraic Seiberg-Witten implies Donaldson invariance. So let's take X be a projective surface, L be a line bundle on X. You can then define an abelian category of L-Bradlow pairs to have objects, a coherent sheaf on X, a finite dimensional vector space V, and a linear map phi going from V into Hom of L, E. So these are related to L-Bradlow pairs in Mocciucci's monograph. Well, K of A is K of coherent sheaves plus Z, where the Z parameterizes the dimension of V. And the coherent sheaves embeds in A as a subcategory of objects in which V and phi are both 0. So it turns out that you can define the reduced obstruction theory in this Bradlow pairs case on an open substack, M dot, which includes moduli spaces of semi-stables if either the rank is positive and D 0, or the rank is strictly greater than 1 and D equals 1. So then the case of rank alpha equals 1 and D equals 1 is going to be special. So we define the reduced permissible classes to be the set of alpha D satisfying that or this. And then if rank of alpha equals 1, then alpha comma 1 is not a reduced permissible class, and therefore its counting invariant can be non-zero. So basically these alpha comma 1 classes in the case of rank alpha is 1 are basically algebraic Seiberg-Witten invariants. And even though they're not reduced, they're independent of stability condition because they happen in rank 1, and you can't split rank 1 into sums of other ranks. Okay, so if we fix some Giesecke or mu stability condition on coherent sheaves in X, there's then an extra parameter you can put into the stability condition, depending upon what you do with the dimension of the V space. So you get a one parameter family of stability conditions on this enhanced category A, which restrict to the coherent sheaves on X. Okay, so it turns out that in some case, if T is very, very negative, then the moduli space is empty. If T is very positive, then this is a stable pair moduli space. So you can use the wall crossing formulae to go from the negative case to the positive case, and therefore the reduced invariant here is determined by some algebraic Donaldson invariant and some lower order terms. And then you can do some, well, basically by playing with the wall crossing formula and the stable pair invariant formula, you can show that rank R Donaldson invariants can be written as a function of rank strictly less than R Donaldson invariants and Seiberg-Witten invariants. And therefore, by induction on R, you end up writing the rank R greater than 1 Donaldson invariants in terms of the algebraic Seiberg-Witten invariants and the rank 1 Donaldson invariants, which are basically counting Hilbert schemes. Okay, so this entire program would work for both B2 plus greater than 1 and also for B2 plus equals to 1, although with different formulae, because in the B2 plus, in that case, you have to use this reduced wall crossing formula. In this case, you use the ordinary wall crossing formula. Okay, so I should say that I've worked out none of the details of this at all, and I'm not clear that I intend to, other than saying that it's possible. But anyway, okay, so let me stop there. And yeah, thank you.
Are there? Yeah, after Paul. Okay. There's a question by Gonzalo in the chat about the equations for the L-Bradner pairs.
Well, so I think the differential geometric version of this would be some kind of Seiberg-Witten monopoles. So there's a nice paper, there are 3 papers by somebody called Zentner, that Yuji pointed out to me. And these are kind of a differential geometric version of the it's an approach to relating Seiberg-Witten invariants and Donaldson invariants via these U of n Seiberg-Witten monopoles. And it's basically, you take a vector bundle, a connection, and some kind of a Higgs field-like term, which altogether satisfy a Seiberg-Witten type equation. And there's a U1 action on these, and then by looking at the fixed point loci, you get a relationship between the Donaldson invariant moduli spaces, which are one of the fixed points, and then something to do with Seiberg-Witten invariant moduli spaces. So, yes, so I think that gauge theory problem should be the differential geometric analog of this this enhanced category A, which I'm talking about here.
There's also quite a large literature in that direction, going back to Pids-Rogatch and Turin, right after the Seiberg-Witten work, and there may much work of Feehan and Lennes. And there's also a kind of algebrogeometric work of Nakajima and others, I think, proving that, maybe this is just for the rank 2 case, proving Witten's formally using, as I understand it, again, the kind of a stable pair setup, like Mochizuki.
Yeah, you're right. And it's just, and Zentner is the thing I've seen, which is kind of closest to what I want to do. But all of these other people are doing something pretty similar.
I was interested in you said that the case of curves was boring, but you have a way of counting semi-stables. So I wonder how that compares with other things in the literature. I mean, for example, if I'm understanding right, if you take the pairing with the relative power of the 2-dimensional class that one has in that situation, you would get so that would be I mean, there's work of Witten, for example, on the volume of moduli spaces. So one would expect that that would give the same as the number that Witten considered. But I wonder if it is.
I don't know about that, but that sounds like an interesting question. So Witten's got a formula which makes sense for stable not equal to semi-stable.
Yes.
Okay.
There's also, I mean, there's something called the Verlinder formulae, which are more the K-theory version. But then there should be some connection through a sort of Riemann rock between the Verlinder formulae and maybe the numbers that you define when you take the moduli space when you have semi-stables.
Mm-hmm. Yeah, sure. Well, and the numbers or the classes I'm defining could just be defined using stable pair invariants in the usual way. So I think if people wanted to understand them, they already would.
Yeah, interesting.
Okay, so Miriam has a question.
Yeah, I have probably more of a naive physicist question. You were alluding to wall crossing formulae for Calabi-Yau fourfolds and work, some recent work on that. But what I would like to ask specifically, I would assume if you focus on elliptically fibered fourfolds, did you think about this special case and how far can one get there? Again, that's from F-theory perspective.
Well, I don't know of anything special about the category of coherent sheaves on an elliptically fibered Calabi-Yau fourfold. Possibly, if you want the elliptic fibers to be very small,
Mm-hmm.
then that would give you, well, so the stability conditions you impose on this would be related to the Kähler form. And so if the fibers are getting very small, then the Kähler form or stability condition is undergoing some kind of limit. And it's possible that the sheaf counting invariance there might then be related to some kind of counting invariance living on the 6-dimensional base. But I think we're very far from actually knowing anything about these things. At the moment, we're still arguing about whether they're actually defined, rather than being able to compute even one example. So I haven't got anything very helpful to say about that.
Thank you.
I have a question. So you talk about that this boundedness, this finiteness of these terms when the two Kähler forms are close.
Mm-hmm.
And can you explain why this is true? Or
well, so what you care about is, well, so if we think about H11 of your, the real part of H11 of your projective scheme, that contains the Kähler form, and then the orthogonal subspace to the Kähler form. And so there's a kind of, in some sense, that there's what you care about is a quadratic form if you fix some Kähler form omega, then you get a quadratic form on H11 given by alpha maps to alpha wedge omega integrated. And that will have signature n comma 1 or 1 comma n. Basically the Kähler form is positive, and then the other direction, the orthogonal directions are negative. I'm talking about the threefold case now, but the same thing will happen. Similar thing will happen in higher dimensions if you look at alpha wedge omega to the n minus 2. So what you need to do is you need to restrict to omega and omega primed close enough that you can kind of compare both of them with the same strictly positive definite form on the H11. And basically, you want to be able to carry out this argument with discriminants, and get there's a Bogomolov thing which will tell you that if something is semi-stable for omega, then its discriminant wedged with omega to the n-2 is semi-stable, and part of the discriminant is a kind of C1 squared term. So you're going to worry about whether C1 squared wedge omega to the n-2 is non-negative or not, or is greater than some bound. And then you have to worry about what happens when you vary the omega. And it turns out that if omega and omega prime are sufficiently close in the Kähler form, then the condition that the integral of C1 of L squared wedged with omega to the n-2 is greater than some bound, together with some kind of stability thing, is, you don't care too much about the difference in the omega and the omega primed. Sorry, it's not very well explained, but it's something to do with that.
Thank you. Are there other questions or comments?
Hey, Dominic, can I ask a question?
Yeah.
Yeah. So the virtual cycle on the strictly semi-stable, like for the threefold or final threefold, Clavier threefold, do you think this is any related to Jun Lee's stuff? Like he didn't construct everything, but maybe for some modular for semi-stable object in the derived category, he used semi-perfect obstruction theory to construct a virtual cycle. Do you think your virtual cycle will match the same thing, or?
Well, I think that's a different thing. It sounds like you're talking about a stable equal semi-stable case. But Jun Lee had a different program in which he wanted to start with something which was an Artan stack. He wanted to blow it up repeatedly until it became a Deligne-Mumford stack.
Oh yeah, he used some command blow up something.
Yeah. So yeah, and you can actually ask the same question for non-Calabi-Yau 3 cases, for example, for sheaves on surfaces or something. And actually the answer is no. That gives a different way of getting counting invariants of strictly semi-stables. If we went back to my formula for the vertex algebra structure, that involved the E and the E dual.
Yeah.
So E is the X complex, E dual, and you have to kind of, well, you have to swap it over basically. Now the my invariants have a property, have this Walkosing formula involving the Lie bracket. The Lie bracket only cares about this kind of symmetrization of the X complex. However, I can show that if you follow this, if you could make this blow-up program work, then the blow-ups you get would depend not just upon the symmetrization, but upon features of the E and the E dual separately. So whatever the blow-up in the invariants you get through following this K1 type blow-up program would be, they have to be more complicated. And they wouldn't necessarily satisfy this Walkosing formulae that I've written down.
I see. You mean their virtual cycle cannot satisfy Walkosing formula results, right?
Well, it would need to satisfy a Walkosing formula with some kind of corrections.
I see.
And the corrections are going to care about the difference between the rank of E and the rank of the kind of, well, the rank of E alpha beta and the rank of E beta alpha, basically. And it would care about the difference between the Chern classes of E alpha beta and the Chern classes of E beta alpha. whereas my thing just lumps those two things together.
Okay, thank you.
Okay, so I think we need to go to the discussion session now. So let's thank Dominic again for a beautiful talk.